So, now what we have seen actually, that we have derived and we discussed about the internal energy. Now, let us have a quick review so far what we essentially have discussed. From the gas kinetic postulates, we said the molecules are solid spheres, we assumed it, but having the very lesser volume of all these molecules in comparison to the overall molecule volume of the gas which is occupied in the cylinder, in the container. And now this spherical balls are colliding with each other, that is molecules are colliding with each other, and they are undergoing the elastic collisions. That means the kinetic energy which is going to be converted to the potential energy is recovered back as soon as the collision is finished. Further, the collisions are instantaneous, that is very fast, and the time spent during the collision is very less in comparison to the overall time where before the collision the molecules spent during the traveling the path and after that. Further, what we say that during this collision, being the perfectly elastic in nature, the kinetic energy as well as the momentum remains conserved. That means, in the collision process the magnitude is not changing, only the direction is changing, and hence since the velocity is defined as both magnitude as well as direction, and we are changing, that the velocity is changing, because magnitude is conserved, that is remains constant, but the direction of the motion of these molecules are changing. Now, after internal energy, let us see what happens the total energy of the molecule, and we will also talk about the degrees of freedom. So, let us say that these molecules are free to do, the molecules of an ideal gas are free to do three kinds of motion, that is a translational motion, a rotational motion, and vibrational motion, that is from their position at the particular stand, how they are vibrating with respect to that location. These all motions gives energy, and we represent as those energies. Suppose if we are speaking again in terms of the Cartesian coordinate axis system, then we essentially says that the total energy of the molecule can be represented as E translational, E rotational, and V vibrational. Now, E translational kinetic energy, we say that can be represented as 1 by 2 mvx square plus 1 by 2 mvy square and 1 by 2 mvz square, where vx, vy and vz are the velocity components of the velocity v along the x, y and z axes respectively. Now, these are essentially three quadratic terms, and hence these three quadratic terms essentially represent the contribution to the translational kinetic energy, and they are termed as, in these three directions, these quadratic terms essentially as in the energy as degrees of freedom. Moreover, for rotational kinetic energy, we can write down that rotational kinetic energy 1 by 2 I omega 1 square plus 1 by 2 I omega 2 square and 1 by 2 I omega 3 square, where omega 1, omega 2 and omega 3 are three rotational speeds along the x, y and z coordinate system. And then again you can say that the molecules at their particular instant at particular location, they also vibrate with respect to that location and gives two more component of energy, and we represent that energy as E vibrational 1 by 2 mx dot, that is dx by dt square plus 1 by 2 kx square. Note that the first term essentially represent that in a generalized coordinate. Note that this is not particularly, we are speaking here the x coordinate system, it is a generalized coordinate. I have represented it as x, and then this is a kinetic energy by how much displacement is happening of the molecule. That means, if the molecule is here, it is vibrating along this position, then let us say if this generalized coordinate is represented x, then x dot naturally gives the velocity and x is the position, and hence this component will give kinetic energy and this component is giving you potential energy, and that is what we have written it here. That is 1 by 2 mx dot square for plus 1 by 2 kx square. Now, all these energies, whether it is kinetic energy, rotational energy and vibrational energy, including all these motions, when we add, we will find in equation 1.59 as the total kinetic energy. Now, what we observe here, a very important fact, that all these energies are in quadratic form. That means all these quadratic energy terms are essentially representing the degrees of freedom of that molecules. And there is a popular theorem in the gas kinetic which says that the sharing of the total energy of the molecule in their respective modes, that is all these vibrational, translational and the rotational components, equal sharing takes place. That means, if we see that translational kinetic energy was 3 by 2 kT, we have already obtained. You note that here, that E translational kinetic energy we have written as 3 by 2 kappa T. This is coming from, that is 3 components of velocities. That means, if equal sharing is happening, then I can say that half kappa T is the component of the energy in each of 3 translational directions. That means, the equipartition theorem says that half kT amount of energy is distributed in all the possible modes, and this is known as equipartition theorem or equipartition theorem of energy. Now, note that the degrees of freedom, as we said, that in the all these are the quadratic terms, whether translational, rotational or vibrational. That means, each one of them denotes the in that mode a degree of freedom. Therefore, let us say if degree of freedom is represented as alpha, that means the molecule is having 3 or any number of degrees of rotational, translational and vibrational, then we can say here 3 plus 2, that is 8. Out of 8, 0 to 8, the alpha can take any of the value depending upon the condition where we are interested in. And then this E internal in the generalized way we can write down as I have written in equation number 1.58 as E internal is equal to alpha by 2, n is the number of molecules, again kappa times T, and this alpha denotes the degrees of freedom. Now, let us move ahead in our discussion, is that since at room temperature, that is standard sea level conditions, you can say, or at laboratory temperature, the rotational and the translational motion will be present. However, the vibrational motion which is related or associated to the temperature, only at very high level of temperature these excited vibrational states are achieved by the molecules. That means, at room temperature we need not consider those vibrational motion and their respective kinetic energy as well as the potential energy. Therefore, at the room temperature we should only consider the translational as well as rotational. Now, let us see some cases. Suppose if the gas is monoatomic, then what we find here, this monoatomic gases does not have any rotational motion, that is along any it is not possible to rotate along these axes, and we are discussing about at room temperature conditions, then there is no vibrational motion as well. Therefore, the monatomic gases has only translational kinetic energy, and hence alpha is written as 3, and then we can say if alpha is written as 3, then this can be written from equation 1.58, which we have just seen it here, that the generalized coordinate system alpha by 2 n kt, then put here 3 in place of alpha, then it becomes 3 by 2 n times kappa times t, and hence we obtain here the internal energy of a monatomic ideal gas as 3 by 2 n kappa t, and inserting the cap n value small n into Avogadro's number Na, and this expression becomes 3 by 2 n RUT, where RU is the universal gas constant, and this is also termed as thermal equation of state of monatomic gases. Likewise, if we observe the diatomic gas like N2, that is N triple bond with N. Now, what happens here in a diatomic gases, if we see, let us say if these are the two molecules here, the two nitrogen molecules which are N here, and this is a diatomic gas. Now, what happens, along this line where the molecules are joining, the line joining these molecules, there is if even the molecules are rotating about this line, their kinetic energy due to this motion is equal to 0. Why? Because if I can write I omega square, where omega is, let us say, in this direction the rotational speed omega, then I is here is equal to 0, which is nothing but the moment of inertia, and hence the diatomic molecules does not have any contribution even if it rotates along the line joining the two molecules. However, there are in Cartesian system there are two perpendicular lines. That means in the, let us say, if this is x direction and y and z, what we observe that in the y as well as in the z direction, if the molecules, that is, if this line joining is moving through the center of mass of both nitrogen atoms, then along the y and z direction there are two contributions. Therefore, we say since two coordinating terms are involved, then we say that there are 2 degrees of freedom given by two rotational motions. And in addition, these group of molecules, these twin molecules can perform 3 translational motions as well, which are free to do those. So, that is, their center of mass is free to move in any of the 3 Cartesian coordinate directions. Therefore, the total degree of freedom for nitrogen molecules at room temperature is 3 translational plus 2 rotational, hence it turns out to be 5, alpha turns out to be 5. Then again, now substituting the same value in alpha by 2 and kt, if we substitute alpha as 5, then it becomes 5 and by 2 and kt, and then it turns out to be 5 by 2 nRUT. This equation is termed as the thermal equation of state of a diatomic gas. Now, moreover, at very high temperature, when the vibrational states are also present, then this number of degrees of freedom will also change, because the vibrational motion will give the kinetic as well as potential energy. Now, moving to polyatomic gases, what we can again find out the internal energy of the gas, and something by we can write down something like a generalized the internal energy is something like again alpha by 2 and by kt. Now, we will see again some more important relations, and we are more extending our discussion, and we will define here the specific heat of gas and their ratios. Please understand, from our school days we have studied this, that the specific heat of a substance is defined as, for a unit mass, if we try to include, that is, increase the temperature of the matter by 1 degree on temperature scale, whether it is Celsius or Kelvin, then amount of heat required under such condition is known as specific heat. Please note that the solids, in the case of solid, the amount of the heat, if we increase the temperature, is not changing either its any other properties, and hence the specific heat for solid is almost remains constant. That is, both pressure and volume are not changed. Essentially, in solid case, the volume is not much affected. However, in the fluids, that is both liquids and gases, the amount of heat required for a unit mass of fluid in SI unit, let us say kilogram or gram, or in the molar units, actually the moles. In both cases, the amount of heat required of this mole or 1 kilogram or 1 gram of gas is that is termed as specific heat. A minute temperature change or small temperature change will lead to a large change in pressure as well as volume. Therefore, unlike solids, which are essentially constant, that is only one specific heat is possible, because temperature change is not going to change much its volume. In the fluids case, the value of specific heat may range from 0 to infinity, that in this interval it can have any value. Therefore, to precisely define the specific heat, we need to fix one of the conditions. That means, we take either we are considering the specific heat at constant pressure or at constant volume. Therefore, the specific heat of the fluids are defined at two conditions, at constant pressure and constant volume. That is why it is termed as specific heat of an ideal gas at constant pressure and specific heat of gas at constant volume, denoted by Cp and Cv. Now, to derive their expression and their relationship, let us quickly review the first law of thermodynamics. For that reason, I have here drawn a figure for you. You can see here that this is a cylinder and there is a piston, and a certain amount of an ideal gas is present here. When the heat is supplied, let us say a small amount dq, and this piston is free to move, then what happens? This dq will be, the heat supplied will increase, some portion of this heat will increase the internal energy of the gas, and then further the remaining portion will push the piston upward, so that this gas, which is considered as a system by this dotted line here, is doing outside or external work to its surroundings. If that work is represented as dW, then from first law of thermodynamics, which is nothing but the conservation of energy, can be expressed as dq is equal to d internal plus dW. Now, since you are here supplying the heat here in this cylinder piston assembly, and the gas is able to do work. Now, let us have two checks as we talked about, because we are interested here in bringing down to our discussion to Cp and Cv, that is at constant pressure and constant volume. Suppose in the first case, if the volume the volume of the gas remains constant despite supplying the heat dq, then what it happens, since the piston in this case at the constant volume, the volume of the gas is constant, the piston is not moving, and hence the external work done by this gas on the surroundings is 0. And in that case, we will obtain from 1.65 will reduce to dq is equal to d internal. Now, since this is happening, this heat is supplied here, dq supplied here at constant pressure, then by definition Cv at the constant volume, the specific heat at constant volume can be represented as the change in the heat supplied at dt, that is dq by dt at constant volume subscript. It is read again, replacing dq with dE from equation number 1.66, we can get d internal by dt at constant volume. Now, from this 1.67 we can write down dE internal as CV dt. Once you obtain 1.68, this expression substitute back to your first law of thermodynamics, that is essentially in 1.65 this equation, and then you will lead to dq is equal to CV dt plus dW, that is 1.69. Now, let us see the second case. If the heat is supplied at constant pressure, what will happen? In this case, in actual scenario, the portion of heat is going to increase its internal energy, and remaining heat is free to do some external work. In this case, again the specific heat at constant pressure, however, the pressure is remaining constant that we are ensuring. In this case, the specific heat at constant pressure can be given expressed as dq by dt at constant P. You can see here the subscript now changed from V to P. And for 1 mole of the gas, suppose from the ideal gas law, PV is equal to RUT, we can RUT, no, I am sorry, actually we can see it here, that from Cp is equal to dq by P. However, this dq which we have obtained from 1.71, you please substitute here in the 1.72. What we obtained here, Cv dt plus Pdv upon dt. Now, since Pdv we can replace using our ideal gas law, and hence here consider 1 mole of gas to replace the value of small n, we will obtain Pv equal to RUT. Now, you please differentiate this thing, and since you are maintaining here the pressure constant, let us see this thing, that if we write the ideal gas law, the original ideal gas law RUT, now if I am considering 1 mole of the gas, then we can write down this PV is equal to RU times T. Please differentiate, then you will obtain dP volume P, differentiation by parts, and then we can obtain here P times dV is equal to RU is a constant, and it will lead to you dt. Now, since the pressure in this case is constant, this is 0. Then what we are left with, P times dV is equal to RU times dt. This expression, if we substitute back to our expression here 1.73, we will lead to Cp is equal to Cv plus Ru, because dt will be cancelling out in each term. That is, this expression what we have obtained is a famous Mayer's relation that says Cp minus Cv is equal to R, or Cp is equal to Cv plus R. Please note here, mathematically right now itself we can see that Cp, that is specific heat at constant pressure, is more than specific heat at constant volume. Physically, how to understand this thing? See, for equal temperature rise, if we are maintaining the temperature rise, what essentially we see that the specific heat at constant volume and the specific heat at constant pressure, they are not same. That means the specific heat required at constant pressure for the same temperature rise is required more, because at constant pressure the heat is not going to increase the full internal energy. It is also consumed in doing some external work. Please note that for an ideal gas, the internal energy, unlike real gases, depends only on temperature. That means what we can say, that the internal energy E for a general gas, that is any real gas, can be dependent upon T, or let us say P, the pressure. However, for an ideal gas, the internal energy is totally dependent upon T from the thermodynamics point of view, and hence since it is dependent upon temperature, therefore for the same temperature rise we can right now see clearly that unlike the constant volume case, where full energy supplied to the system is increasing the internal energy at a particular, to achieve a particular temperature of the gas, for same temperature, we have to add some more amount of heat to have rise, and that is why Cp is more than Cv. Now we will move on this discussion. Now, since we have brought out the Cp and Cv, that is constant pressure and constant volume, the specific heat, their ratio is denoted as gamma, and this is very important parameter in the kinetic theory of gases and dealing the compressible flow as well. This is the ratio of Cp by Cv. Now let us discuss that out of this monatomic, diatomic and polyatomic gases, what are the respective ratio of specific heats. Please recall back that E internal, we brought out that E internal is equal to 3 by 2 RUT from the equation number 1.63. Let us go and quickly review it, that we have brought out here the equation number 1.63 for internal energy of a monatomic gases. We have written here 3 by 2 RUT and RUT, and since here only 1 mole is considered, therefore we have written 3 by 2 RT or RUT. Hence, one more results here we see here, that we write here E internal is equal to Cv into T. Please note that unlike a generalized case is that if dE we are taking the partial differentiation, then we write down Cv and dt. This is a generalized result we have just obtained, and we know this thing for any gas. However, if we integrate here, then we will get E minus let us say integrating dE is equal to Cv is a constant and dt. Let us say we are integrating from 0 to t, and hence let us say E0 to some value E, then it leads to you E minus E0 and Cv, and say let us say rather than 0 we are seeing the let us say 0 and t, and then we can denote it here Cv T minus 0. Conventionally, at 0 temperature, we discussed it that the internal energy in an ideal case, that is for an ideal gas, is 0, and therefore E turns out to be directly Cvt. Therefore, please note here that for ideal gas, the internal energy expression of dE is equal to Cv dt, a general expression, as well as a particular relationship E is equal to Cvt, both are valid. And that has been essentially used here, that E internal is equal to 3 by 2 RUT is can also be used with, if we replace Cvt, then immediately brings down the Cv is equal to 3 by 2 Ru. Now using the Mayer's relation, Cp minus Cv is equal to R, we can say that Cp is equal to 3 by 2 Ru plus Ru, that is 5 by 2 Ru. Now ratio of specific heat for a monatomic ideal gas can be written as Cp by Cv, the from 1.81 5 by 2 Ru, and then 1.80 say gives me 3 by 2 Ru, and then it turns out to be 1.67. Likewise, if we talk about the ratio of specific heat of a diatomic gas, we can observe that E internal we have written earlier 5 by 2 RUT. Now again using the expression E internal Cvt for an ideal gas, we bring down Cv is equal to 5 by 2 Ru, and hence Cp from Mayer's relation is brought out 7 by 2 Ru, and taking the ratio is comes out 1.4. Note that air is also, though it is composed of many gases, but due to oxygen and the nitrogen, the major portion of these gases are diatomic. Therefore, air is also assumed as a diatomic gas, and hence in compressible flows we use the ratio of specific heat of air more frequently 1.4. Further, to generalize the ratio of specific heat relationship, let us consider a polyatomic gas, and we have seen that E internal energy for a generalized case is alpha by 2 and nkt, and then and or that is essentially reduces to alpha by 2 small n RUT, and since we are considering 1 mole of polyatomic gases, it turns again using the ideal gas relationship CVT and then alpha by 2 RT, and hence T and T both sides will be cancelled out, and then we are left with CV is equal to alpha by 2 R. Likewise, using the Vermeer's relation, the Cp expression can be obtained as alpha by 2 plus 1 Ru, where again alpha is here, the degrees of freedom of polyatomic gases. Now, taking the ratio gamma is equal to Cp by Cv, we will get here 1 plus 2 by alpha, a very famous relationship which we are again and again we are coming across which. Now, please see that at room temperature a rigid polyatomic gas has all the 6 degrees of freedom, that is the 3 translational and 3 rotational. Hence, inserting alpha is equal to 6, the gamma turns out to be 1.33. Now, we have discussed about the ratio of specific heat for monatomic, diatomic and polyatomic gases. Now, we move on to discuss and we will try to see a very important concept which we keep coming across whenever we talk about the fluid dynamics. When the fluid is air for aerospace, as such as in aerospace sciences, we talk about aerodynamics, or in gas dynamics. That concept is the continuum hypothesis. Let us understand what is a continuum hypothesis. We keep saying that consider the media, that is the fluid medium, as continuum, a continuous media, and then we define the various macroscopic properties such as thermodynamic property, viscosity, thermal conductivity. All these are associated properties we used to define. But what is a continuum hypothesis? We must understand first. See, all the matter are at the microscopic level. Now, we have understood that they are made of the various molecules, and we have seen that these molecules keep colliding with each other and they do the random walk. The random walk means they, as we said in our last talk, that whenever in the molecules we start seeing it, that is we have tagged the instant, it picks up any direction and move. In the path, when it follows, that is a linear straight line path following the Newton's law of motion, whenever it collides with another molecule, and then we define it that in 2 successive collisions or 2 consecutive collisions, the average path travelled by this tagged molecule we have termed as mean free path. In such a situation, if we analyze that, okay, we have taken such a unit cube where this tagged molecule and other molecules are also are present there in the cube, and then we try to see that in the fluid we try to see either microscopically or macroscopically, both, that is at the molecular level or as an aggregate or averaging the thermodynamic property, whichever method we adopt, and write down the governing equations, such as in microscopic case the Boltzmann governing equation, Boltzmann equations, or in the macroscopic state the conservation laws. If we calculate the thermodynamic property, that is the pressure, temperature and density, both will be same. So, it means either approach we follow, we are going to have the same thermodynamic properties or the flow properties. It means what the continuum hypothesis is that it allows us, and it eases our work, that considering individual molecules and writing the Boltzmann equation for each and every molecule, which are in very large number for a small fluid lump even, fluid mass even, then it eases that we, rather than considering that those individual molecule, we can consider as a fluid mass as a whole, and then we average the properties and we calculate. That means continuum hypothesis eases, but how? since the mean free path is there, then what we find, suppose if a unit cube or a cuboid we are taking, and such that in that case, suppose if the flow domain we have chosen something like this, where L is the length, B is the breadth, and we are considering, let us say this is a thickness, here I am denoting as a height h, such that the length is greater than B and greater than h for this domain, flow domain. My flow domain chosen is such like this. What is happening here, the minimum length or is the height here, the minimum dimension of this flow domain is the height. My mean free path, that is the molecule's mean free path in this domain, must be lesser than the minimum dimension. Then we say that the molecules can be assumed as the array of molecules or the myriad of molecules can be assumed as a continuous medium, and then we can define the properties. At the ground level, in ground level at the standard sea level condition, what we observe that all the molecules, rather than going and perceiving them individually, we can consider a fluid mass as a whole and we define the properties. In this case, any fraction of molecules if we observe, since the mean free path is much lesser than the characteristic length, the minimum characteristic dimension of the medium of the container where the fluid is contained or occupied in, then the collision of these molecules with the wall will not be distinguished by the wall. That is, two successive collisions, the wall cannot distinguish in between them. So, what it feels, a continuous collision, and hence we say the fluid medium is continuous. While in the different application, such as in the uppermost layer of the atmosphere, where the atmospheric gases are rarefied, there the molecules maintain their distances very far apart. That means they start retaining their individual identities. In such a case, since the mean free path becomes longer and longer, and when it becomes much more than the characteristic dimension of the flow domain, then in that case, whenever the molecules go and collide with the wall or the surface of the body which is immersed in that fluid medium, then the body surface or the wall can distinguish the two successive collisions. In that case, we say the containment hypothesis breaks down. In non-dimensional form, the ratio of mean free path lambda and the characteristic dimension, let us say small l, is denoted as a non-dimensional number called the Knudsen number. And based on Knudsen number, we can define some flow regimes, like here. You can see here I have given that when the Knudsen number is less than 0.01, then we say the fluid as a continuum flow regime. However, in some scenario, when the Knudsen number is greater than 0.01, but it is less than 0.1, then this is called a slip flow regime. When this range of Knudsen number is between 0.1 to 3, then we call it as a transition flow regime. And finally, when the Knudsen number is more than 3, then this is called as the free molecular flow regime or rarefied flow regime found in upper layer of atmosphere. Now, it means at the ground level or at the upper atmospheric level, what should be this chosen size of the volume which I have just talked about, that let us say call it control volume and denoted by a let us say symbol, let us say delta V. What should be a typical size? What should be a typical size of this control volume, so that we can consider, and when we define the properties for this control volume. In this control volume, the fluid properties or the thermal properties, thermodynamic properties, whatever we define, what should be typical size? It has been experimentally proved that to answer this, as low as the typical volumetric size should be 10 to the power minus 9 millimeter cube is that typical size where a sufficient number of molecules as many as 3 into 10 to the power 7 are always present, so that we can assume the fluid medium as continuous. So, it means if this is putting as a limit, then it means you can see that this can be precisely understood by this graph which I have plotted for you. That is, in this domain what we see here, that this del V naught is nothing but 10 to the power minus 9 millimeter cube generally or approximately, which contains this sufficient number of molecules. It means more than this, any domain whatever we select and we define the properties, they are essentially constant. What does it mean? Slightly more if we elaborate, we see that if a fluid medium, if we keep cutting, subdividing the fluid medium, then whatever the property we have defined for the original medium, if we divide the fluid medium in various parts, then those thermodynamic property or flow properties are essentially again will be constant for these subdivisions. But if we keep on doing this exercise continuously, then there will be a limit comes which is nothing but your del V naught, beyond which if we subdivide the flow domain, then these properties will not be will not be further constant, and they will start changing, because in such a situation as low as del V naught, the control volume size, the required number of molecules which is composed inside this del V naught will not be constant, and any removal of the molecules from there, because they are always in random motion, and this control volume is nothing but a hypothetical boundary we have assumed. So, when some molecules move out, the density started changing. The density of such control volume is defined as the, let us say, rho is equal to some limit where L is small l is a characteristic length, and we define del m by del V. For example, to understand it better why this happens, let us say that a flow is taking place, there is a sphere inside the flow, and with the upstream velocity UA, that is the free stream velocity, and let the dimension of this sphere is d. Now, what happens when the flow moves over the surface, then in the forward region the flow try to retard, and because of this, in this domain somewhere in the forward side, the flow start compressing. However, as soon as it moves, the flow finds expansion, undergoes expansion, and then further at the downside it again experiences the compression process. That means if any domain we choose in the forward region, then we essentially using this relation, that is rho, at any particular point, let us say r t, where here it is denoted by, let us say for example, I am interested in some point P. At this point P is somewhere here in the compression zone or expansion zone, or in the forward and the rear side compression zone. In that domain, if we are interested in defining this property, that is density at point P, then let us say position vector of point P is r at any instant t, then we can say rho RT is equal to limit L tends to 0 del m by del V, where L denotes, small l denotes the characteristic dimension of that domain which has chosen. So, it means if this domain selected which is enclosing this point P, where we are interested in evaluating the density, if it is in the forward zone, then it is overestimating the density. Whereas, when we select the domain somewhere in the expansion side, it is underestimating. However, if the domain is dense enough so that there is a sufficient number of molecules are present, then whichever location the domain will be present, it always gives you the same value of the density. Moreover, if the flow is incompressible, then in that case, since the density is not changing, then in that case, wherever the flow domain we select, it always gives you a constant value of density. Therefore, this compression, expansion and compression process, what we are talking about is essentially for our discussion interest, that is for compressible flows. Now, what we further see it here from the below graph, where I have plotted here, let us say density, and then with respect to the volume under consideration, the control volume under consideration. What we find here, that this C1 represents the flow domain selected in the forward side. C2 is the flow domain in the expansion, where the expansion is taking place. So, it means the above graph, it is going like this, and the lower graph is going like this. The above graph C1 is actually overestimating the density, and then C2 is underestimating the density. However, there should be some lines or some curve like this, which actually represent a definite value of density, which is dense enough, and that value will come, which is assumed experimentally proved that is as high as or as low as, in both the cases, either we are going this side, so as low as, here as high as in the back side, that this is 10 to the power minus 9 millimeter cube approximately, contains 3 into 10 to the power 7 number of molecules. Therefore, for a continuum hypothesis, this rule must be valid, and then whatever thermodynamic or flow properties we calculate, that essentially remain constant, even if you subdivide, that is up to level beyond or more than del V naught. Now, let us go ahead further. When this continuum hypothesis breaks down, as we just said, this continuum hypothesis breaks down when we remove a group of molecules from this minimum control volume, so that the density start varying. Then we said, in this case, the mean free path becomes much more than the characteristic dimensions. It is usually found in the upper layer, where space shuttle, for example, the space shuttle flying, then even though the molecules are there, are having a very large distance between two consecutive collisions, that is mean free path is almost is order of even the total length of the spacecraft. Therefore, this gives a very important information which we must understand at this juncture. It is said that in the upper layer of the atmosphere, we experience this cooling. Have you ever thought of this, that even though in the rarefied atmosphere, a rarefied level, in the below atmosphere or the ground where we all breathe and live, we find the sun rays to be very hot if we spend some more time in the direct sun rays. However, a dense atmosphere is always present above us, whereas if the astronauts are there in this space and they are walking, let us say, out of their space shuttle, they should experience more heat than us, because they are in direct sun contact and there is no atmosphere or very rarefied atmosphere which is enclosing them, but still they experience the cooling, that is, they experience that the temperature is very down, it is not high. The reason is, since the surface or their body surface, whatever the molecules are going and hitting, between two consecutive collisions, a lot of time is spent. That means the body clearly distinguishes between two collisions. That means essentially we cannot justify that, we cannot essence that a temperature over there, because the collision frequency is very less, and in turn when it happens we experience cooling. However, a vice versa case, a reverse case happens at the ground, where too much collision frequency happening and the molecules are coming and hitting us, the warm air, and we experience heat. Now, at the Knudsen number for our compressible flow, since the Mach number and Reynolds number both are important, the Knudsen number is given by an expression which is given here. Knudsen number is equal to 1.26 square root of gamma m by Re, where m is the Mach number, Re is the Reynolds number, gamma is the ratio of specific heat of the gas, and Kn is the Knudsen number. Please note that here m by Re is greater or equal to 1 is basically for a rarefied gas flow. Here we should understand a rarefied flow or free molecular flow is always having a low Reynolds number. However, in the ground flow or in the high speed flow, which is, let us say, hypersonic level, where the Mach number is more than 5, and simultaneously rather than low a high Reynolds number is also present, then in that case the expression for Knudsen number is given is something like Kn is equal to m by square root of Re. These expressions are very much important in solving some problems actually based on the Knudsen number, based on the Reynolds number and Mach number. Now, let us move on the perfect substances. So far we have already discussed that assuming the matter, that is the fluid in our case, is as the ideal. Now we will try to proceed towards the actual cases, which is that this ideal, which we termed as an ideal case, in the real life we know that these ideal are just idealization of a substance, and in real cases this always does not hold. However, we should understand this fact also, even though this is a hypothetical case, highly idealized conditions, and we derive or analyze the situation, then how could it can be related with the real gases? With the actual substances of the solid, liquids or gaseous, if we try to write down the governing equation explaining the phenomena of these states of matter, then it will become a cumbersome task or almost impossible to solve those governing equation. Rather, if we assume the substances to be perfect, then it gives very simple mathematical expression, and then using the experiments for actual substances, we can insert the correction coefficient to define from these obtained governing laws or expressions to evaluate, to define the flow behavior for real flows. For a perfect substances, it is described by two main properties, that is termed as the rigidity or shear modulus, and second property is called bulk modulus. The shear modulus is denoted by N and the bulk modulus is denoted by K. Now, to develop the expression for shear modulus as well as the bulk modulus, let us understand using these figures. I have drawn a figure here. This is the shear force acting on a unit cube in the fluid. On this unit cube, for this unit cube, I am considering the front face of this cube, which is of length obviously L, because all the sides are equal. Then if the shear stress is applied at the top surface, and suppose that the substance is moved, the side moves a distance small delta L, then it means the side is rotated with an angle alpha. Therefore, The shear modulus or rigidity is defined as shear stress upon shear strain. When the shear stress is tau and the shear strain of this side is delta L by original length L, then this becomes tau upon tan alpha. For small rotation, that is from angular rotation when alpha is small, then we can say from trigonometry that tan alpha is almost equal to alpha. Therefore, the shear modulus or the rigidity can be defined as tau upon alpha. Now, apart from the shear stresses, there would be the compressive stresses also acting upon the matter. Now, if suppose in our case, which is the compressive stress which we are interested in, the pressure. Here, when the pressure is applied here, let us say in the form of compressive stress, because it is compressing the fluid, and we know that pressure is always acts towards the fluid, that is on the surfaces which is compressing. In this case, suppose a unit cube of the perfect substance is chosen and the hydrostatic pressure, that is the fluid inside the river or ocean we are considering. In that case, if the hydrostatic pressure P at this side and in this fluid, if we take a small fluid lump where the pressure is varying from P to dP, that is P plus dP, a small variation in the pressure, and due to which, that means if P was applied and we increase the pressure from P plus dP, a small increment in dP in the pressure, such that the volume shrink. If the original volume was V, then it shrinks to V minus dV. In that case, what happens? The change in the cube volume will become minus dV by V. Why minus? Because when you are applying the hydrostatic pressure, the volume of the cube shrinks. Then the fractional change in volume is minus del V by dV by V, whereas the increment in pressure is dP. Therefore, the bulk modulus denoted by K is defined as dP upon minus dV by V, which essentially can be written as K is equal to minus volume times dP by dV. The reciprocal of the bulk modulus is termed as a property called compressibility. This is very important for compressible flows. Therefore, the kappa denoted by kappa, please do not get confused with Boltzmann constant. This is the, again I am defining with Greek letter kappa as a standard notation, which is the reciprocal of your bulk modulus capital K. And hence, I can write down the kappa is equal to minus 1 by V dV by dP. Now, since the density is equal to 1 by specific volume, where V is specific volume, then we can replace this thing, and essentially the 1.100 equation becomes K is equal to minus 1 by rho d rho by dP. This compression process, please note, that depends upon the process through which it is carried out. If the compression is carried out retaining, that is maintaining the temperature constant, the bulk modulus is termed as isothermal bulk modulus. And if the compression is carried out keeping the entropy constant, that is you are not is inserting any disorder into the system, then it is called isentropic bulk modulus. And both are represented as Kt, which is represented as isothermal bulk modulus, and Ks is termed as isentropic bulk modulus. And then Kt is equal to minus V dP by dV at constant T, whereas it is minus V dP by dV at constant S. If same way, since the compressibility is the reciprocal of the bulk modulus, likewise the compressibility kappa T and kappa S are also defined, which are just reciprocal of this. Now, let us see the cases. Since we talked about a complete matter, the perfect matter, perfect substances, now let us see the states of matter, that means perfect solid, perfect liquid and perfect gas. By definition, the perfect solids are those which has both non-zero bulk modulus, shear modulus as well as non-zero bulk modulus. In the perfect solid, when these are experiencing the external stresses which are compressing, then internal stresses are generated, which in turn is compensated by the external stresses are compensated by generating the internal strains. And according to Hooke's law, where it says that the stresses applied are directly proportional to the strain generated within the solid. Therefore, a perfect solid says that suppose if the stresses are denoted by sigma,